Hi, welcome back to AP Physics C, Electricity and Magnetism, Unit 2, Conductors, Dielectrics, and Capacitors. So the first topic is going to be focused on conductors, and what we're going to do is we're going to break this into two separate videos, one focusing on the electric field, and then the other focusing on the electric potential. So let's get started talking about electric field in a conductor. So the main thing is when we look at electrostatics with conductors is that there's 4 rules that you need to remember. The first rule is that the electric field inside a conductor will be 0. So what happens is if I place a conductor, again, so a conductor is basically a metal, right? And we're looking at those free electrons. So the free electrons, they're able to move nice and smoothly. There's no impedance and so forth. All right, so if I place this metal in an electric field, again, so this would be the positive side, this would be the negative side. The charges will align in such a way that the negatives will align towards the positive side and the positives will align towards the negative side, thus creating a big hole where the E field is going to be equal to 0. That's the first rule. And then in fact, rules 1 and 2 kind of work together. So any excess charge from inside, so those charges that get pushed out, will reside on the surface of the conductor. Okay, so again, if I draw another conductor, if I have a positively charged conductor, all that charge is going to sit on top of the surface, okay, where we know on the inside our electric field is going to be equal to 0. The third rule is that the electric field on the conductor is going to be perpendicular at the surface, or just above the surface. Okay, so here's my E field coming off. It's going to be a perpendicular vector that's perpendicular to the surface. Okay, and we'll say just above it because once it gets past it, then it starts doing all its bending based on what's around it. The final rule is that if the conductor is irregularly shaped, the charge will accumulate points with the smallest radius of curvature. So if I have a conductor that looks like a teardrop, the majority, right, is going to align towards the top, right, and it's going to be spread out along the way. Okay, because when we look at the charge, it's going to be a charge density, right, where the area here is smaller than the area towards the bottom, and so that's why you're going to have more charge at the top per area. Once we get diving into calculations, a couple things are going to be big here. So that surface charge density, it's just going to be the E field over epsilon naught, but we know that it's also equal to Q over A, which then leads a lot to, so most of the time we'll talk about spheres where the surface area is 4 pi r squared. And then Gauss's law, so Q enclosed over epsilon naught is equal to the integral of E dot dA. Okay, so that's going to be very important in our problem solving process. So sometimes, if it's a non-sphere, then applying Gauss's law is very important. But a lot of times with a sphere, you can also just use KQ over R squared, right? Because that's a point charge. But a point charge we assume to be a sphere. And then a special application of using conductors and E fields is Faraday Cage. And so this kind of so if this is a conducting material and I put it in an E field, kind of what happens with these, right, charges, they're going to align in such a way, right, that there's a counter E field inside the conductor, right, that opposes what's trying to pass through it, and it's going to cancel. But also, in addition to canceling inside the conductor, it's actually going to cancel it in that void as well. Okay, so some Faraday cages. So this is the reason why they say stay in your car in a lightning storm, because the car acts as a Faraday's cage. Okay, in a lightning storm. All right, so you have this metal, right, which is what a conductor is, being struck by an electric field, which is what provided by the lightning. And so it's going to have it pass around and everything, and then what's inside the car is going to be safe. So let's look at an example, and something that's very common on the AP Physics C test. You have a conducting sphere inside a conducting shell. Okay, so the 8 coulomb or 8 microcoulomb sphere is a conducting sphere, but then we have it inside like a basketball, right? So we have like a lacrosse ball inside of a basketball. Okay, some things to note: the radius of the sphere is 2 centimeters. I'm going to mark these because it's very important, because there's a, if we find a question, right, if it talks about finding the E field at a certain point that's less than 2 centimeters, well, the E field is going to be 0 because it's inside the conducting sphere. If it's inside the shell, if it's between 4 and 5 centimeters, well, the E field is going to be 0 because that is a conducting shell. So let's figure out the E field. So it's going to ask us to find the E field at 4 places: 1 centimeter, 3 centimeters, 4.5 centimeters, and 7 centimeters. So A and C are very easy, right? So for A, the radius is 1 centimeter. Well, that's inside the conducting sphere. So that tells me that my E field is going to be 0. C is at 4.5 centimeters. Right? Well, that puts me inside the ring, or the conducting shell. And so because I'm inside a conducting shell, my E is also going to be 0. Now that leaves B and D. Okay, so B is at 3 centimeters, which is somewhere outside the conducting sphere. So if you apply Gauss's law, right, so we say Q enclosed over epsilon naught equals the integral of E dot dA, right, and you go through and follow, well, the E field's constant, so it's E times the integral of dA. Well, the A is going to, if we take the integral of just A, or dA, it's just going to be A. So we're going to end up with E times A. But A, it's a sphere, so the surface area of the sphere is 4 pi r squared. Okay, and so then we can go and solve it for E. So I have Q enclosed over epsilon naught equals 4 pi r squared E. And now all I have to do is divide by 4 pi r squared, and guess what we end up with? KQ over r squared, where this Q is the Q enclosed. And so now we can just plug in our numbers. So we would have K, 9 times 10 to the 9th. Q, you do have to be close, you have to be careful, you have to convert that microcoulombs. And our R is 0.03 squared. Okay? Know that it's given in centimeters, that needs to be in meters. And we get an E value of 8 times 10 to the 7th. Sorry, it's a little sloppy. So it's 8 times 10 to the 7th newtons per coulomb, right? So that's out to 3 centimeters. And now part D says 7 centimeters. So here's my Gaussian surface, right? It's a Gaussian sphere. So note that we're doing the enclosed charge. So what's enclosed? We got negative 4 microcoulombs and positive 8 microcoulombs. So our enclosed charge is going to be positive 8 microcoulombs minus 4 microcoulombs, which gives us plus 4 microcoulombs. But all I have to do is the same thing here as I did in B using Gauss's law. And so it's just going to end up being KQ over R squared. So 9 times 10 to the 9 times 4 times 10 to the negative 6th divided by 0.07 squared. And we should expect this to be less because we're further away. Okay, even though we're further away with less charge, and we end up with 7.35 times 10 to the 6th newtons per coulomb is our electric field. Okay, so this kind of configuration is very common on the AP test. They're going to ask you different things, but they may also ask you talk about electric potential, which is going to be the focus of the next video.